Hello, hello everyone. I'm Taemin Lee, who is presenting motion sickness prediction in stereoscopic videos using 3D convolutional neural networks. The others are Taemin Lee of Yonsei University and Jong-Chul Yoon of Kangwon National University and In-Kwon Lee of Yonsei University. Motion sickness is one of the major obstacles to the popularization of the VR system. With the VR system gaining popularity, the incidence of visually induced motion sickness can also increase. Therefore, it is important to quantitatively confirm degree of motion sickness caused by viewing VR content. Recently, there have been some studies predicting the degree of motion sickness using a machine learning-based method. This study predicts the degree of motion sickness using a decision tree, using velocity and depth as features. However, it is necessary to consider a deep learning-based method which shows better performance in various fields than the exacting machine learning-based methods. And this study uses the deep autoencoder model to predict the degree of motion sickness. However, this is a method that can only use the velocity as a feature among the main factors affecting motion sickness. We used a dataset published in the paper of Padmanabhan et al. This dataset consists of 15 training videos and 4 test videos. The length of each video is 60 seconds. Each video has the degree of motion sickness computed using the SSQ and MSSQ shorts measured with the user's view fixed. As we need a greater amount of training data for our deep learning model, we used the data augmentation method. The first method used was frame shifting. We assumed that the motion sickness induced after watching 56 seconds of a video is equal to the motion sickness induced after watching 60 seconds. And we extracted 1 frame per 0.5 seconds, resulting in a total of 120 frames from a single video. Therefore, by shifting the start frame one by one, we can obtain 8 different image cubes from 120 frames for a single training video. The next method used was pixel shifting. We assumed that methods such as rotation and scaling can affect the degree of motion sickness, but the motion sickness induced by watching a video is the same as that induced by watching a few pixel shift videos. As can be seen in this figure, the difference in shifting of 5 pixels is difficult to distinguish from human eyes. With this method, we are able to increase training data 3 times. This is an overview of our method. We compute the optical flow map for velocity feature, disparity map for depth feature, and saliency map for eye movement feature for each frame sampled in the video. The obtained maps are collected into 3 image cubes and input into different 3D CNNs. The features computed from the 3D CNN corresponding to each map are concatenated into the input of the fully connected layer. Finally, the degree of motion sickness is computed as the output of the system. This model is trained by using the mean square error between the output and ground truth sickness as a loss function. 2D CNN extracts features from the convolutional layer using 2D convolutional operations with a feature map and kernel. And a 3D CNN model extends 2D CNN to an additional dimension. The 3D CNN computes convolutional operations in a video, not only in the horizontal and vertical directions, but also in the time direction. The structure of all 3D CNNs are identical and can be observed in this figure. A 3D CNN consists of 4 convolutional layers. Each convolutional layer has 32, 32, 64, and 64 filters respectively. The size of the convolutional corners is 3 by 3 by 3. After each convolutional layer, we use ReLU as a non-linear activation function. And all max pooling layers have a corner size of 2 by 2 by 2 and a stride of 2. This table is the results of 5-fold cross-validation using only the training dataset. The results show that by using our 3 feature maps, our model wanted to predict the degree of motion sickness similar to ground truth sickness. This is a comparison with previous study. The left side of our method is the case of using only optical flow and disparity maps in the same way as the previous study. And the right side is the case of using all 3 maps, including the saliency map. This is the figure of visualizing absolute error in sickness prediction results. Our method using all 3 features showed the lowest error in all cases. This table shows the root mean square error of the model of a previous study and our models with different combination of feature maps. We also computed the Pearson linear correlation coefficient to determine whether each model predicts the sickness of the video in accordance with the tendency of ground truth sickness. This table indicates that our method using 3 feature maps has the smallest error and strongest correlation. We compared the performance of models with different numbers of filters of convolutional layers to determine the most suitable 3D CNN structure in our method. The comparison models were the models in which the number of filters of each convolutional layer is reduced or increased by 4, compared to that in the proposed structure. The model of the proposed structure showed the best performance. We also compared the 3D and 2D CNN-based methods in order to confirm that 3D CNN shows better performance by considering temporal domain information. The 2D CNN-based model for comparison was constructed on the basis of the model used for video classification. The high-level features from the 2D CNN of each frame are used as inputs to the fully connected networks. And the 2D CNN model does not correctly predict the degree of motion sickness in the video than the proposed 3D CNN-based method because temporal domain information is not considered. And it can be observed that the salience map plays an important role in predicting motion sickness. This figure shows that the examples of salience maps for turnovers and cartoon coaster videos. The salience area of the turnover video is centered, whereas that of the cartoon coaster video is scattered. This is consistent with previous studies which indicate that separation of eye movements by fixation can significantly reduce motion sickness. When only velocity and depth are used to predict the degree of motion sickness, we cannot consider the user's eye movements. In this paper, we have proposed a 3D CNN-based method to predict the degree of motion sickness using optical flow, disparity, and saliency map. Our first contribution is to propose a more advanced running model to more accurately predict the degree of motion sickness. And our second contribution is to enhance the accuracy of motion sickness prediction by adding a salience map as another feature. Our limitation is that the degree of motion sickness predicted by our method is still differed from the ground truth sickness in some videos. And also, unlike the general VR system, the data set we have trained was the user's view was fixed. So our future work is obtaining sufficient data sets. For this purpose, we may consider using biometric data of users watching the video. We can also consider a model that predicts the degree of motion sickness more accurately using factors other than visual elements such as field of view and latency of display. Thank you.
Thank you. I have one question on the Slack, but does anyone else have a question they'd like to ask first? Okay, so the question that someone typed in here was, why was a 3D CNN picked over a RNN, a recurrent neural network, since the latter seems more common for video processing?
In the paper, we discussed that point. We just compare the, we wanted to compare the previous study, and the previous study using 60 seconds. So we must train that in 60 seconds. So, but RNN means 1 second, 1 second, 1 second. So we just try 3D CNN, and we also compare the 2D CNN based model.
Okay. As a follow-up, how do you think on a different data set, how do you feel like the RNN would work versus the 3D CNN, if you weren't as concerned about comparing it to the previous study?
That's a good question, and maybe later it is worth to trying and for comparison. But we in the paper we try more fewer frames, and 3D CNN can also predict the motion sickness. So it is good worth it to later comparison for comparison.
Okay, good. Thank you.